Who's going to win? No betting, please. No betting allowed. Who will win? Gas car versus electric. Whoa. So this is an example of acceleration. The green thing there receding into the distance is the gas car, and the camera's on top of an electric car. And partly this is an effort to dispel this notion that electric cars are slow and boring. Electric cars are very fast off of the line. They don't have the top speed that some of the gas cars have, but in the quarter mile, electric cars are very quick, and they have monstrous amounts of acceleration. I just wanted to start my video off with that. So what we're going to be talking about is accelerations. Now, what I do if we were in class is I would show you these equations. If you look on this left side, these are all of our equations that we've discussed so far. We have displacement, final minus initial. We have velocity. This is average velocity, a change in displacement over change in time. And this is our equation for acceleration. And these are all what I would call our average formulas. Now, you can find the average acceleration over a certain amount of time, or the average speed. And we've talked about this, driving from here to Waco and back. You can figure out what was my average speed over the whole trip. But what if I wanted to know my speed at any one moment as I pass a certain point on my trip? What was my speed right then? Or if I get pulled over at some point, right? The cop says, I clocked you 72 in a 65. Uh-oh. That's something called instantaneous speed, which means right now. What is your speed right now? Or how far did you go right then? And these average formulas don't work. So here's what I do if we were in class. I'm just treating this like if we were in class. I'd have you write these down. So these are facts. Write them down in this particular order. Equation 1, equation 2, equation 3. Do it. Write it. This x should be delta x. I messed that up. I couldn't figure out how to cram the little delta in there. This is delta x. Now these look scary. And when we don't know where things come from and we're seeing something for the first time, it can often be scary. I'm hoping that you know what all these little things are, though. You know what v is? Velocity. You know what a is? Acceleration. You know what t is? Time. So that's what all that stuff is. These are the equations that we can use if we want to know the instantaneous values for something. If we have something flying or driving or running and we want to know right now, what time did that happen? What was the acceleration right then? What was the displacement? Okay? These equations are the ones that will do it. These won't, right? These are our average over a period of time. So these instantaneous ones are the ones that we use for a lot of problems because they tell us right then. V equals V naught plus AT. Change in displacement. This is really x final minus x initial equals V naught t plus 1/2 AT squared. V final squared equals V initial squared plus 2a delta x. Those are your three instantaneous equations. I know them by heart because I do a lot of physics, and you may need to commit them to memory because it will be helpful. Now, they are found somewhere. If you Google AP Physics 1 equation sheet, it'll pop up. This is the equation sheet you'll use on the test. And if I can zoom in here they are. You see those three right there? There they are. Those are the same equations that we just messing with. There they are right there. Now you see how they're a little different? You see these little tiny x's? That means in the x direction, left and right. If they were y's, that would mean we'd be going up and down. We haven't really talked about up and down yet, and we will. I need you to just see that they look a little different, okay, versus what I've written here. They're a little different, but they're the same thing. For equation number 2, I like to put both of the x's on the same side. This is x final minus x initial. College Board puts x final on this left side and puts x initial on that right side, and I don't know. Yeah. If I took this and subtracted to that side, I would have delta x on this side. Same thing here. They write it x final minus x initial. I write it delta x. But it's the same thing. The equation sheet can also be found in our class. In the very first blob of stuff. AP1 Physics equation sheet, right there. So just know that this is stuff that you need to know and be able to use. Now, let's talk about where do these come from. It's tempting to think that these equations are made up by some nerdy guys and gals who want to scare the crap out of us and make our lives difficult. And while tempting it may be, they're actually naturally occurring. So let's think about that lab that we had you guys do at your house. And we'll change things a smidge. Let's say that we have something that we're going to test. And let's say that it starts at a low speed, not 0 speed, that would be down here, but it starts at a lower speed and ends up at a higher speed. This low speed down here we could call V initial or V naught. This higher speed we could call V or V final, or something like this. So we have an initial speed, we have a final speed. This initial speed is going to be at time 0. And this final speed is going to be at t. We'll just call it t. Okay? So, we can graph something that has an initial speed that's not as big and a final speed that is much bigger. Something is picking up speed. This is something that is accelerating, right? So that's a thing. Now, whatever that thing is, we have graphed it. What is the slope of this graph? It's a VT graph. So what does the slope mean? Slope is rise over run. I can pick 2 points. I'll pick this point and this point. So what's my slope? VF minus VI, or V naught, divided by T minus T naught. So what I have a slope that is change in V divided by time, and that is acceleration. Okay? That's the slope of my line. Now remember, we're just graphing something that was moving and that picked up speed. And we get this equation. That equation looks familiar, right? Gee, it looks a lot like this one. Now, what I'm going to do next is I'm going to do some math here. I'm going to multiply both sides. So let's get rid of this word that says slope for a second because it's in my way. What I'm going to do here is I'm going to multiply both sides by t. So I'm going to multiply this side by t. I'll multiply that side by t. The t's cancel here. So now I have something that says v final minus v initial equals a times t. Got it? Made that a little prettier. So I multiplied t on both sides. Now what I'm going to do is I'm going to add my colors seem to change every time I do something. I'm going to add the initial v to this side. What equation do I get? So I move v to the other side. I get this. V final equals v initial plus at. This equation is this equation. Okay? So what I'm just showing you that these are naturally occurring. That when we graph things, when things move and we graph stuff, these equations just come out of those graphs. Okay? That's a thing. In fact, what I would do, I can find the area under the curve of this big shape by making part of it into a rectangle. And I could find the area of that rectangle, and then part of it into a triangle, find the area of that triangle. And the neat thing that happens is when you find the area under this whole shape here, the combination of those two shapes, the area will end up with, you'll end up with this equation right here. And we don't have to do it because you don't need to see all of it, and our time is precious. You see how this is 1/2 AT squared? What is the area of a triangle? It's 1/2 base height, right? Okay. So you kind of see where that starts to come from. 1/2 base times height. 1/2, I don't know, base height, So that's where these come from. These equations are naturally occurring, and we use these a lot. And we're going to talk about how do we use these. I'm going to give you some strategies for using these.